While I thank the organizers, I can thank them twice. Once for inviting me here, and second for sending me Tel Aviv's Gillard Luhrmann, whose thesis I will discuss today. So the issue that I will be addressing is to develop some sort of geometric language for sets that is parallel to what we saw in Rafi's talk. And the approach that I'm going to talk about today, I'm only going to talk about the very beginning of this approach, is something that grew out essentially from an attempt to literally translate theorems through a dictionary and to develop some sort of effective mechanisms for example, as was raised at the end of the last talk, giving an effective Sharpe theorem. So we've been talking about learning to walk before we run. Today's talk should be viewed as learning to crawl before we walk. Okay, so what we're going to do is look at this picture, and at the end, what we want to see is some version of how you would take this picture, but think now not of a picture of a set and breaking the set into some sort of essential elements plus a residual component, and then perhaps repeating this description, and we'll see that we actually get some reasonable results. So of course I have now, oh, there it is. So let us start at the end here. This is what we're going to be aiming for, and even this I don't think I'll be able to get through, but here's the kind of dictionary we'll be talking about. So last talk was, or at least some portion of it, the simple portion is on the left-hand side here. So that is, you have a function, you have wavelets, which is a particular kind of orthogonal basis for L2. Then you have the wavelet coefficients, and when you have a basis, you can express the function in the basis by computing coefficients, and then you have the standard theorem about the L2 norm of the function. Now, on the other side, you have sets or measures. So what do I mean by measures? You can think of a measure as giving a set. That's the support of it, in whichever sense you mean. I'm actually going to be talking not about a topological support, but a measure theoretic type of support. Now, if we go down the left-hand side, what we're talking about is some sort of multi-resolution analysis where you fix a scale, 2 to the minus n. You look at your function at each scale, and the way you do this is you localize, and you just compute what happens locally. Now, on the right-hand side, even the first entry here may be artificial. So why should you approximate by hyperplanes? Well, it may not be the appropriate thing to do. It's the thing you're trained to do in calculus, of course, because you take a graph of a function, and you're told that if this function is the kind you study in Math 101, then there's a tangent. And this tangent is given by epsilon delta arguments. But this is, of course, only appropriate in certain questions. Now, there'll be a formal definition of something corresponding to a wavelet coefficient. These are historically called beta numbers. There's nothing special about beta. Historically, they come after alpha, though. That is the reason they're called beta. And now the point is we want to be able to do the following, and this is not a well-defined problem. We have a set, and we wish to understand this set. So what do you do if you're a statistician, for example? You fix unit scale, and you do some sort of L2 approximation. Well, that's fine, but this is some sort of global picture. Now, of course, you can say, all right, then you should localize. Okay, maybe you don't look at unit scale. You should chop into several boxes, and you look locally, and you just do some sort of statistical or geometric approximation, and you get, again, undergraduate statistics. And now the point of the left-hand side is there's a way to synthesize the function through the local behavior. And we're searching for some sort of synthesis, but it's not clear exactly what one should do. And of course, it's dependent on the problem. So you might think that the ultimate thing is to parameterize your set. So, and that this would provide a full understanding. So of course, this is incorrect. The parameterization could be just as horrible as the set itself. And you don't gain anything by doing this, but that's a possible goal. And it's some sort of good reference point to keep in mind. You might also just ask some simple question about the size of the set, where size could have any one of a number of definitions. C is, you might, for example, be fixated on Hausdorff dimension. And it's a legal occupation. And it could be the correct thing to do, and it might not. And then you have a whole host of things you want to do. One of the things I'm going to just try and explain is Gillard Luhrmann's thesis, which does some sort of synthesis of this type, where you take the local information and then you fit it back together across all scales. And instead of talking about L2 norm, the thing that will replace energy, it's not obvious you have an energy here, but this is d-dimensional Hausdorff measure, but you should not think about d-dimensional Hausdorff measure. You should think about length, arc length. So it's sufficient for our purposes just to think of arc length. And in fact, all the theorems that I state will go through jacking up the dimensions. And you don't usually think of length as an energy exactly, but this is the tack I want to take today. D equals 1 is what you should think. Okay? Think D equals 1. Think D equals 1 in 2 dimensions, and already you have a lot of problems. So let's see. Now I will turn this off and try to explain. Could I have some help, please, in raising the screen here? So don't worry. It's all taken care of. It's all taken care of. You're way behind me. Okay, so while this is being raised, let me talk about some of the issues that you would like to address. So you should be thinking that our ultimate purpose is to describe some extremely complicated set in high dimensions, where high could mean 10, or could mean 100, or could mean 1,000. Now, the sort of standard thing that one does now is that one searches for some sort of local plane, and you project the set. You just project orthogonally onto this. And there are all sorts of theorems about what happens when you have a nice smooth object, or a smooth object crossed a Cantor set. And the point is that if you leave this smooth category, all these projection theorems fail violently. They just completely fail. And if you're a mathematician, I could show you in the discussion maybe, the instant you pass from C1 plus epsilon category to the Lipschitz category, or C1, projection arguments simply fail violently. So you cannot project and argue simply in this manner. The other point is that you should think that this set is poorly defined. It's a data set, for example. It has noise on it. And so some of the pictures I will show you have actually noise built into them at some point, and then there's a program to take them away. Your program should be insensitive to noise. This corresponds to in some sense picking a residual as in Mandrel. So, and the other thing we should be thinking about is statistics. That we want some statistical description here. Now where does all this come from? It's nice to give some slightly historical background talk. And please at this point do not object. So I'm going to write things up that may violently affect your sensibilities. Please hold on for just a minute, okay? So in terms of analysis, the objects that I'm going to talk about come historically from an attempt to understand potential theory. And I really mean very, very classical potential theory. You have a surface in R3, you put an electrical charge on it. Where does the electrical charge go? The answer is we don't know where it goes. We know this much better in 2 dimensions, but even in 2 dimensions, it's really a tough problem. So I can only draw the pictures in 2 dimensions. You should think of there being some underlying set K here, and we want to do some sort of potential theory on there. Now let me stick to 2 dimensions and cheat a little more. So I will have functions on K, maybe on L2 with some measure, and I'm going to map them to the convolution with 1 over z. So what does this convolution mean? There's some measure in the background that I don't wish to specify, but it might be naturally related to the geometric structure of K. And what we do here in this game, let's call this T. And then the question is something like the following. The most elementary question is you study the L2 norm for some measure, and you want to see if this is bounded, independent of the function, by the L2 norm of the function you start with. So this is, for the cognoscenti, this is the theory of layer potentials. This is one way of doing theory of layer potentials. And the vastly simplified version is you want to do something like this, and this will allow you to invert an operator when you get a result like that. Now, then what happens is, so we understand a lot about this operator now, after the activity of the late 70s and 80s, and that is that there's some way, it's rather canonical, of writing this convolution. Oh, by the way, what you should be thinking, what did I do?
Just the question.
Oh, I forgot that. I thought we were in Spain. No, this is the universal mathematics. This is the question. Okay, so it's self-adjoint. Yes, it's self-adjoint. Maybe with a minus sign, okay? Now, what happens is, how do we understand this simple operator? This simple operator, by the way, is nothing but the Cauchy integral if you have a curve. You'd have a function defined on a curve, and you integrate f of zeta d zeta divided by zeta minus z, and then you have a 1 over 2 pi I. Okay? And this is some question about the boundary values of this operator. Now what happens historically is we understand that this operator splits into a diagonal term plus an off-diagonal. The diagonal term corresponds to the place where, roughly speaking, K is flat. And therefore the off-diagonal term is an expression of the local lack of flatness of the set, K.
So f is characteristic function of K?
F is any function.
But I mean, in this statement.
No. No, in this statement I'm asking whether for all functions in L2.
Well, the measure lives on K.
The measure lives on K. And I did not specify the measure. You should think of the measure as arc length measure for a reference point. This is the interesting category, actually. Now, this off-diagonal term, it turns out, is well understood historically. It corresponds to what is technically called a paraproduct. And now, if you go and investigate this paraproduct geometrically, you discover that this paraproduct corresponds exactly to the Pythagorean theorem. Okay, so now the left-hand side probably didn't get people to yell at me too much, but now there's going to be a right-hand side. And I will put the classical traveling salesman problem. Think of this in R2, okay? Don't yell yet. So the classical version of this is you have endpoints and you look for the shortest Hamiltonian cycle. Now, so an analyst looks at this and says, what is this endpoints? Right? You can ask the same question about an arbitrary set, a completely arbitrary set. And then the question to the analyst is there even a curve of finite length that goes through this? Sometimes yes and sometimes no. If you have the unit square as your set, you need a curve of infinite length. You need some sort of Peano curve. Now what happens here is that we have a notion of flatness, and the set K, roughly speaking, has a flat piece plus a non-flat piece. This only makes sense on each scale. At a certain part of the set it looks flat on scale 2 to the minus n, and on a certain piece it does not. And if you translate here, you get some funny statement about a set K. And now you try to run, let's just try to run a shortest curve through it. So if you want to, you can think of minimal spanning tree or Steiner tree or whatever. But let's just strip away the verbiage. We're trying to run a curve through the set. How short can this curve be? And then we have a theorem, which is actually obtained from analyzing this situation historically, and that is that the length of the optimal curve has the same size, that means up to a universal constant, as certainly the diameter. This corresponds to the diagonal term of t. Well, then there's some other stuff, and there's some sort of energy, which I just write in this form right now. Let me write optimal here. Okay? So if you're a computer scientist, you may not like this because you say, I have a polynomial time algorithm that will do this anyway. This is an order n log n, or if you do it right, even order n algorithm. And what it does is it exactly synthesizes information from the local scales. It puts it all together. And so there is no theorem yet, all right? Because I have not defined the terms. I have to draw a picture. So I'm going to draw a picture now to explain the theorem. So here's what we're going to do. Q is a cube, which in 2 dimensions is a square. And we're going to pick dyadic cubes. So the side length is 2 to the minus n, where n is any integer, positive or negative. And now here's what we do. We take this cube, and we want to see how flat the set is in here. So we have some set, and we just look at K. Actually, I don't want that one.
So flat means looks like a straight line.
Flat means exactly looks like a straight line. How much does this set look like a straight line? So here is Q. And how much does it look like a flat line? Well, I try and find a best approximation L. And here's now a definition, which you should note if you're dealing with data sets is a horrible definition because it's completely unstable. Nonetheless, it is a mathematical definition. So we take the infimum over all possible lines of the supremum of Z in the Q, and in K. So just we throw away the rest of the set outside here. And now we look at the distance, the Euclidean distance from Z to the line L, and we're now going to normalize by the side length of the cube. Okay? So in this picture, we're just looking, after we pick a line, for the worst point. Here it is. And we're computing this distance, and now we're rescaling. So this number is dimensionless. This is just a dimensionless number, which is redundant, right? And this is simply some number between 0 and, it's actually a half. Let me write 1, because we set 1/2 equal to 1. Okay? If you get 0 here, either there's no set at all, or your set lies in a straight line. And if you get 1, well, that could happen if you had an extremely dispersed set. And then what we do is we take this sum here over all possible dyadic squares of all sizes. So for each grid size, we do this computation, and then we end up with this theorem.
What is L of Q?
Side length of Q. So think of L of Q as 2 to the minus n. So here is L of Q 2 to the minus n.
What is this approximation? Is up to a constant?
Up to a universal constant.
Depends on the dimension or nothing?
That is a very good question. It should be independent of dimension. I cannot prove that. It should be independent of the dimension you are in. Actually, there are many other interesting questions on a computer science level about this theorem. For example, what if I want constant 1 plus epsilon? How do I adjust this? So I could discuss this.
Say something trivial. I mean, you want this sum to be finite in order for the curve to exist.
Yeah, and the thing. Yeah, no, it's not vacuous. It's the statement that the length is infinite.
Yeah.
You might be happy with the statement that the length is infinite.
Just to be for clarity.
Yeah, for clarity. Okay, I'm sorry. I wasn't striving for that. I was. Okay, now, so then we have this peculiar situation. It's slightly more complicated in the 80s, where this understanding arises, and then this idea turns out to be, it's quite an elementary idea, you see here. What's surprising is how many open problems could be solved with this. So, just to give you a list, Serge Lang calls this proof by authority, right? You make a list of impressive sounding topics and then you say, I did this, all right? But it's supposed to indicate that there must be some physical mechanism going on here with rather wide applicability. So in the theory of singular integrals, what's that? That's objects like this, where you integrate against the singular kernel. Study of Brownian motion, various geometric properties, conformal mappings, potential theory, Kleinian groups, hyperbolic 3 manifolds or hyperbolic n manifolds, and you should think of base note of Laplacian here, for example, and certain technical versions of curvature. Although you should think in the world we're living in also, curvature is infinite everywhere. This is what you should think of. Okay, now having this theorem as some sort of guide, you might ask, what can we do a la Fourier analysis here? So we should criticize this theorem, first of all. It's completely unstable, this thing. If I add in another point, maybe I have some huge set and I put in some outlier, the number pops up to 1. Statistically, this is irrelevant, but your definition has to deal with this. So here's the way out that I'm going to describe. We're just going to redefine this now. This is an L infinity definition. I want to put in an L2 definition. And the L2 definition is just going to be some sort of linear regression. It's just undergraduate definition for each scale. So we're going to have a square or a cube. And now we replace this L infinity definition by erasing here. And we should integrate over the square. Now we should square this. And this then will define the square of the object. And now there's going to be a measure in the background. So there's a measure floating in the background here. And we're just going to replace the L infinity definition with the local statistics of this measure. So when you're doing this in dimension 1, you can think of this as just finding the principal axis with respect to this measure for the measure restricted to a cube. Now I've also lied here. You're supposed to expand this cube by a factor of 3, but that is just a technical detail. Now let me write down Gillard's theorem, and then we're going to turn to some data sets. All the data sets we're going to see are going to have some sort of physical meaning, and it's therefore natural that this kind of dictionary could be helpful. So here is a weak version, I just state a weak version of Gillard's thesis. That sounds bad. Weak version of Luhrmann. He's not weak. Okay. So we have now this new definition of beta, the statistical definition, and what we are given is not specifically a set, but we're given a measure mu. Let's normalize to make it a probability measure, and you should think of this on the unit square. Now, where does this measure mu come? It's perhaps a data set, and you have some weight on the data points. You might think of, for example, and it's completely sufficient to study this case. You could think of this as just a sum of Dirac masses, and the theorems will be neither harder nor easier for that. So we have just a collection of n points. You take mass 1 over n at each of them. And now, you see we can do the following. Let's take a point x in R2, and there are, at various scales, one box, generically just one box containing the point. So here's Qn plus 1. Here's Qn. It's twice as big. And then this one has a box Qn minus 1, etc., all the way up. So we have this infinite number of boxes. You should think of this actually as a large number of boxes. Like, in this case, you would have log n scales as the relevant effective threshold. And now what we do is we assume as the hypothesis that whenever we take x, we look at all the cubes, so we look at all scales, and we compute beta squared of this, and we assume that this is bounded by some constant A, which is independent of the point. Now, then what I want to say is that there's an effective means of parametrizing the set by a one-dimensional short object. So there's going to be a Jordan curve. You should think of this as a Jordan curve. It's just a rectifiable curve. And it's going to contain most of the measure. So it will pass through.
Just for almost all x?
For every, there are various versions. In the weakest version, I would just take it for every x. But there are versions in L1, for example, which is more interesting. And then the Sharpe theorem is the following. How much of the mass can you pick up in short arc length? So the Sharpe theorem is there exists a curve gamma such that two things hold. First of all, the length of the curve is small. How small? E to the universal constant times A. Two, how much mass lies on this curve? A large amount, but not that much. E to the minus universal constant times A. So all the constants are universal, and you simply cannot improve this theorem. I just stated the one-dimensional version of this. There are, of course, versions of this passing canonically defined surfaces through a big piece of the measure, and they all have the same form. So this turns out to be it has quite a complicated mathematical proof, but the proof is rather irrelevant. So I want to show you, just to end this, a description of what one can do with even this very simple notion.
It's true for all dimensions, yeah.
This is true for all dimensions. So you have the dimension of the ambient space, you have a set in Rn, and you have a dimension d, which is what you're approximating by. No. Nothing depends on mu. Oh, the beta, I'm sorry, yes. The definition of the beta just comes from this.
So everything depends on mu?
Everything, no. You're given a measure mu, you're given, say, a collection of data points, and it satisfies this condition. And then the conclusions are independent of the measure. All right? In fact, the theorem is much stronger because it exactly describes what happens in these cases. Why are these bounds best possible? Okay, now we can start. Sorry. So now I'm going to show you some slides that Gillard made, and I'm going to show you rapidly three kinds of data sets. How much time do I have? 15 minutes. I'm going to try to do a sensation and stop before my time. Okay? This is not a statement about my professional identity, by the way. So, we're actually going to show you three examples of data sets, and we're looking for some geometric structure. We're going to impose this multi-stage and multi-scale algorithm. And here is a very simple picture that we'll analyze. Notice that the picture over here on the Fourier analytic side is much more complicated. Much more complicated. And this picture, for those of you in image processing, you will note that this picture, which is known as Paulina, must be phony in this presentation, because how is this picture generated? It's generated by a Fourier analytic argument, okay? But I needed a picture. So what we're going to do is just look at these notions of beta, which will come up again, And we'll see what we can do when we pick apart the various dimensionalities of this. Now, actually, what you should really think of is that you are presented the picture in 3 dimensions. And you just have the data set, and you wish to go and reconstruct maybe by hyperplanes. And then surprising things happen when you do that. Here's a second example, which is much loved. This, I'm going to show you some currency. This is a very popular picture in American, well, actually in all universities. So this is currency over a 10-year period. We're going to be looking at 5 currencies: Australian dollar, Japanese yen, Deutschmark, British pound, Swiss franc. So my apologies to the local hosts. And this is a much abused data set. So here I have to apologize.
I don't understand this. I mean, you have 3 dimensions for the 5.
This is a projection. I just had to project the data. It's a 5-dimensional data set, and there's some choice of principal axes, and I just projected it because this is all I can do. All right? But you should think of this as a 5-dimensional picture. So first I wish to apologize. So notice what a good student I have. All right? Let's recall the definition of beta. So what we are given now is a cube or a square and a set. So I told you there was some technical thing about tripling the cube. So here's what we're looking at inside, and then perhaps we triple it. And the wavy set plus the lines is the set we're looking at. And there's a measure on this, which you could think of as arc length measure in this case. So that's what we're given. The set, we pick a scale and a location, and we get such a thing. And now we search for the best line, best L2 line. And this, of course, requires that we have a measure on there. And we just find it. By the way, of course, this L2 line is not necessarily unique. Yes?
Use L2 geometry, on the other hand, we take cubes rather than balls, yeah, instead of straight.
It's a very interesting point, actually. And this is actually the computational issue that arises in higher dimensions. We don't know what to take for any effective representation. The only reason, you can, of course, do everything here with balls, and there's no change in statements.
Goes, it changes.
That's right. That's right. So there's some dimensional changement, but all the theorems hold with other theorems, and we don't know how. The nice thing about dyadic cubes, though, is you see it's much faster to compute because you're just computing to precision epsilon log 1 over epsilon terms. Okay. So now, again, he's really a great student. So now, for each point x, we look at all the squares on all scales, or the ones we have control over, and we sum this L2 beta. And it measures, in the case of one-dimensional approximation, the rectifiability around x. And now we're going to think about mandrel. So I'm going to impose something slightly artificial. But this is kind of a reasonable thing to do if you have a data set. So if the set has some structure, don't know how visible that is, you just stop at scale 1. It depends on your problem. Every problem is different. But for example, suppose your set looks statistically just like a straight line with a very small error. You stop. You say, I understand this set. It looks like it lies on a straight line. And then I could project it onto that line maybe and do some statistics. But you
can list the notions of structure in your head.
You can list the notion of structures. And you can be a fish. You don't need a hand. Right? Okay, and now, so step 1 is you should think of, that's classical statistics. That's the role of statistics. You decide what you want to do on unit scale, and if it's done, you stop. But generically, this is not the situation we're in. So we compute these beta numbers, and now what I'm going to do is look at the various values of this function which occur. All sorts of values arise for different portions of the set. And now I'm going to take my set, and this is a rather artificial one, but one chosen for exposition. You can simply look at the maximum and minimum value of this function and chop off in the middle. You take the mean value and you say the stuff that lies below is rather rectifiable and the stuff that lies above is rotten. Now when you do this, then you get the following decomposition of your measure.
Two-dimensional object, this picture, or multi-dimensional.
You should think of it as multidimensional. Okay, I just made it in 2 dimensions because it's much simpler. Okay, so what we get is some breaking up into a 1-dimensional piece. The eye, of course, does this quite naturally. And a higher dimensional piece, 2-dimensional piece. So let me just show you what one does in an automated fashion. One computes this number, sum of the beta squares over all scales. And now if you make a histogram,
how do you take measures? So the lines have delta measures.
so the lines are data points. I just took pixels. And in this case,
If more concentration on the rest, otherwise it will be invisible.
that's right. That's right. Oh, but I made a, yeah, so,
Just to put more measures.
so by the way, I made a mistake in my definition, and this actually points it out. You're supposed to renormalize this definition of beta for every square, so you have to renormalize the measure to be a probability measure by just dividing this measure of the square. Okay. Now this is what is done in Mandrel. So you have, so in Mandrel, this piece corresponds to the 300-to-1 compression picture, and this corresponds to the residual. Now you can repeat this process. And you break up this image and this image by just repeating. So we have this natural tree structure, which is what you do all the time in computer science. And you break up the left-hand picture into 2 pieces and the right-hand picture into 2 pieces. Let me it's kind of hard to see this, so let me show you the full picture. So we've broken up the set. This is the more 1-dimensional piece, that's the more 2-dimensional piece, and then we repeat. By the way, at this point you actually have a very interesting psychological observation, which I don't have a perfect explanation for. These are the 2 pieces that the eye really recognizes. When you look at the data with better resolution, what you discover is that this piece and this piece, the eye doesn't really need. You take the bad piece of the good piece and the good piece of the bad piece. Now, in this case, one could explain exactly why this happens, because this is a rather simple picture. But I think there's a whole game there. Now, so let us leave this picture and go to a different picture. This can be equally simple. But so I've been talking about approximating by 1-dimensional pieces. Why should you do this? So I want to talk about this. Okay? So if you look at this, it's got some 1-dimensional pieces. Here they are. And it's got some 2-dimensional pieces. Of course, this depends at the scale. It depends on the scale you're looking at the object. But when you get rather close, this looks linear and this looks planar. Let's see what happens if we apply this simple algorithm here and look at 1-dimensional pieces and 2-dimensional pieces. So this is a graph of a function. Now the wonderful thing about this function is it is actually a logarithmic potential. It is an electrostatic potential, and it is an equilibrium distribution. And it is the graph. So you're looking at the graph in R2 of z to the 4th minus 1 to the 1/4. So this function looks like 0 around the 4th roots of unity. And it has some other behavior. If you take the logarithm of this expression, you get a logarithmic potential. It actually comes from what's technically known as Fekete points for the circle. They're actually distributed. And what you see in this picture on the top, you see these little circles around the center. Those are the level lines of the potential. this tells you that in a lightning storm you should sit in the center of an electrical box. And you notice it's flat there. It's completely flat. So that has a physical explanation. And now, so what's nice when you prepare these things, there's inevitably an error. So now when you looked at the one-dimensional piece, so just this and this, and do this decomposition, this is supposed to be the more one-dimensional piece. This is supposed to be the not one-dimensional piece, the higher dimensional piece. But you see this sort of fringe around here, and you think you've made an error. But the program simply detected an error in the way the data points were distributed. It turns out these data points were more heavily weighted around the circle. We went back and looked at it. And therefore, this edge effect is not artificial. It's just the data set that we're given was picked up. So the top picture is just what happens when you do this one pass with one dimension. And here it is when you approximate by planes. So we're in R3. We have a graph of a function. And you see that, of course, the picture picks up some sort of flat area. It picks up that. And it picks up some little edge like this, which is on there. And then it detects that, you see there's some problem around here. And here there's a mixture which actually looks somewhat three-dimensional when you're down close to it. So that's just expressing that. Let's go to a more controversial.
So what is the difference between these two resolutions?
Oh, these are not different resolutions. The top pass here is done with dimension 1. You approximate by lines, and here you approximate by planes. What's much more interesting is to take the picture of Paulina, to represent it as a three-dimensional data set and run this algorithm with lines and planes. And then, much in the way that Rafi's picture gives you pointillism or Van Gogh, you discover certain natural cubistic type algorithms that are used in painting. So there's a way, for example, remember these paintings around the turn of the century where you take a person's head and you open it up, a la Salvador Dali or something horrible. Okay. Now we're going to look at exchange rates. So these are just currency exchanges for a 10-year period. So the data set, now I put at the top. So this is, now actually this is kind of a hilarious example. This is supposed to be, I asked for a 6-dimensional picture, and this is what I got. It's projected on, so 2 dimensions, of course. That's the top K, so this is these currencies. There are 5 currencies over a 10-year period, ending about now. And then there's actually a 6th component, which is called the dollar basket. Now the dollar basket is a linear combination of the other components, so it's irrelevant. So it's actually a 5-dimensional data set. The algorithm has no problem with this because it recognizes this linear structure and ignores it. It just automatically disappears. So how many minutes do I have now? 2 minutes. Okay, so let me just go through here. So this is a very controversial data set. Right? There's a Nobel Prize in economics for a false model of this, just not this year, but the year before. This model is not just wrong, it's quite violently wrong. And all the proponents actually have now given up on this. They say, well, it's an approximation. Now, if you are, for example, a trader, what you might like to do is get some understanding of this data set. Just say, I mean, what do these people do? They just do some sort of statistics. Here's a way that you can do it, and you get kind of surprising answers. Now remember, there's a 5-dimensional set projected into R2. These false models actually make an accurate prediction. Brownian motion is transient in dimension 5. And therefore, you should expect a Jordan arc. And this actually is, if you look at it, you get a Jordan arc. because the approximation which I'm making fun of is not that bad an approximation, it's just wrong. Okay? And what happens is if you want to segmentize spatially, you end up segmentizing in time also because of this Jordan arc property. So what we do is we run these L2 betas, and now, so you have a 5-dimensional set and you're approximating on all scales. It's a little more difficult. And then there are two ways to do this. So here we first pick 1-dimensional approximation, and here 2-dimensional. It's hard to see very much difference. You don't see a lot of difference between the two pictures when you divide up. It turns out this is happening in R5, and what we're doing is you should think of doing principal component analysis in R5. That's exactly what we're doing. So it turns out that this data set does, in an automatic way, a certain segmentation. And roughly speaking, what happens when you examine this picture, I don't want to get into this picture too much because I don't want to make astounding claims, but you see some unexpected phenomena which I don't completely know how to explain, which is that the dimension switches from rather 2-dimensional to rather 1-dimensional in well-defined intervals. And there's some segmentation on different times. So there's a 10-year period. It turns out it just breaks automatically into 4 time scales. One of the time scales, if you want a reference point, corresponds roughly to the period around the crash of the British pound. Okay.
It's particular time months, not the time scale. It's actually different months.
Time periods. So now if we look at these, so it turns out it breaks up by this analysis. You do both 2-dimensional and 1-dimensional analysis. And then you discover that if you take these various time periods, it breaks up into 4 time periods. And then each one has a dimension associated to it, and you break up according to this dimension, and you see actually sort of interesting patterns, many of which have explanations in hindsight. Okay, so I just showed. Let me put some final summary here. So the point is, we want some sort of effective theory. This effective theory should, for example, include Sard's theorem in an effective version, and it does. There's a perfect mathematical theorem there. And that's in fact one of the cornerstones of this, is to understand exactly what the effective version of Sard's is. Not sets of measure 0 or measure 1. Where are these sets? How big are they? And we strip away the requirement that we're dealing with smooth sets because we want to be able to deal with noise. And the approach here is a multi-level or multi-scale approach. And then these things approximate. So having said this, is this truth with a capital T? No, of course, it is not truth with a capital T. But what's quite surprising, I think, is if you think of it, where else would you start? Right? You have some data set. What are you going to do when your colleague comes to you and says, I have a picture of turbulent flow. I just took a picture of this. It's in R3. It has 512 by 512 by 512 pixels. So that's 130 million pixels, and I have this picture formed from it. What can you tell me about it? So the answer is you say, well, why don't you go look at it? And of course, that's what people do. So one of the and now there are many structures embedded in here. There are 2-dimensional structures. There are sheets, and there are vortices, and there are all sorts of things. Another example you should think of, which is kind of a funny one, since we discussed before astronomers, is think about astronomical data. So you have these huge, huge star atlases. And then there are violent arguments, actually mainly between Princeton and Yale, about how to interpret the statistics of these star distributions. And it's peculiar that no one does this because, for example, if you want to find strings of galaxies, how do you do it? The answer is now you go and you look. You go like that. So this is just an indication of the kind of problem and the kind of preliminary approach that one has developed, which should be viewed as complementary to the Fourier analytic. And you should notice also that many of the pieces on the Fourier analytic side are simply missing. Thank you.
Thank you.